Hi there. In this video, we're going to be talking about line integrals around a closed curve. If you refer to one of the previous videos, we looked at how to evaluate the integral of some region bounded between two curves. If we take, for example, 2 points A and B, and there are two curves linking these 2 points, one curve at the top and one curve at the bottom. The bottom one is g of x and the top one is f of x. And the two x coordinates of these points are x1 and x2. And what we wanted to do was determine the area between these two curves, or this area in the middle. We saw that this is equal to minus this integral, and we put a little circle inside the integral. And that circle actually represented that we're integrating firstly along the bottom curve between x1 to x2 like that, and then we integrate back from b to a along the top curve. So it's along an anti-clockwise direction that we're actually integrating in. And the area in question is given by y dx, and we saw that this is actually minus, firstly along the bottom curve, the integral from x1 to x2 of gx dx, then the integral from x2 back to x1 of f of x dx. So the question at this stage is, in the same way that we evaluated a area between the two curves, can we actually integrate a line integral? So instead of determining the area between the curve, can we integrate some function between these 2 points a and b? Can we somehow integrate a line integral from a to b and then back from b to a? So the answer to that question is yes. So let's just remind ourselves what a line integral is, which we saw in the last video. It's just literally some function that's integrated between 2 points. For example, O to A, and the line integral is simply some function. We could think of it as perhaps ft being integrated between O to A and along the length of the curve, O to A. And this is also equal to the integral of p dx plus q dy. So what we would actually now need to do is apply this to the closed curve. There's our 2 points A and B. We want to integrate some function from A to B and then another function from B to A. So this is different. This is not the area between the curves that we're evaluating. It's the line integral along this entire curve. So one property of line integrals that's very important to take note of is that we can only evaluate the line integral between 2 points of a curve if it is a single valued function. So take, for example, an ordinary curve like that. If we draw a vertical line, we can see that it only cuts the curve once. So that's a single valued function. On the other hand, if we have something like an ellipse, and if we draw a horizontal line again, you can see that it's cutting the curve at 2 points. So this would not be a single valued function. So the question is, how do we get around that situation? Well, what we have to do is we have to split it into two parts. So we would have to evaluate a line integral from a to b, and then again evaluate the line integral from b to a. So if we have a line integral and we simply evaluating it y dx, so maybe this y dx just corresponds to p dx, where the function, instead of some other long function p is just equal to y. So this would have to be firstly the integral, the line integral from a to b of y dx, then the line integral from b to a of y dx. So in a general form, we would just substitute p dx plus q dy. So this is from a to b, and then the integral from b to a of the same thing, p dx plus q dy. So I think that this concept is best illustrated through an example. Let's say we have a function that we're integrating. In same example, p dx, instead of p dx, we'll just have y dx. So we want to take the line integral of y dx along a certain curve. So this curve is actually a circle. It's a circle of radius 2. Okay, that does not look as if it has a radius 2. But anyway, I think we get the idea. So that's 2, minus 2, 2, and minus 2. So with the circle, we have two halves of the circle. And you can see that this is, of course, not a single valued function. So what we'd have to do is integrate two parts of the circle. We'd have to integrate perhaps the top half, and then we have to integrate the bottom half. We know that the formula for a circle, or the equation of a circle, is given as x squared plus y squared. In this case specifically, it's equal to 4, since the radius is 2. This 4 is r squared, and r is equal to 2. So the top half of the circle would correspond to the y values associated with that part of the equation, and of course the same is true of the bottom as well. So we'll have to solve for the equation of the circle and just express it in terms of y. And when we do that, we have y is equal to 4 minus x squared and the square root of that. So the top half of the circle is the square root of 4 minus x squared. Sorry, perhaps I should just write plus minus here. And the bottom half of the circle is minus the square root of 4 minus x squared. So now we can evaluate our line integral because we have y. Y is just plus minus 4 minus x squared. So we substitute that in and then proceed with the integration. Firstly, we have to break it into two halves, from 2 to minus 2, and then from minus 2 back to 2 again. So let's just draw the arrows. So we're integrating in that direction first, top half, and then the bottom half. So let's do this. So the top half, we're going from 2 to minus 2 of the function y. And the top half is given as square root of 4 minus x squared. That's 4 minus x squared dx. So this is what we're doing, evaluating the line integral. And then we're going from minus 2 to 2 of minus 4 minus x squared dx. So the first thing that we're going to do is try to simplify this integral to make it a bit easier to integrate. And of course, we know that it's easy to integrate if there's a zero involved, because it just means that there's less terms to evaluate. So that's what we're going to do. We're going to firstly swap this order of the integration. And when we do that, we of course need to change the sign. So this goes from a plus to a minus. So that's from minus 2 to 2 of 4 minus x squared. Okay, bring that minus to the front in the second term. This is also from minus 2 to 2, and that's 4 minus x squared as well. Let's not forget the dx. So you can see that the first term is the same as the second term. So it's just the same as 2 of the same integral. essentially minus 1 minus 1 gives us minus 2. So now we just split this up again just to make it a 0, so that we have a 0 in the integral. So that's minus 2 into, firstly, minus 2 to 0 of square root of 4 minus x squared dx, plus the integral from 0 to 2 of 4 minus x squared square root dx. So there's some symmetry involved here. So if you look at the circle, of course, integrating from 0 to minus 2 is the same thing as integrating from 0 to 2. So what we have on the one side, we should have on the other side as well. So what we're saying is that these terms of the integral are actually equal. So that term is actually equal to that term. So in the same way, we'll just add them together. Okay, so 1 plus 1 is 2, and then 2 times 2 is 4. So we'll have a minus 4 in front of the integral, and we'll have it from 0 to 2 of 4 minus x squared dx. So all we need to do at this stage is just evaluate this integral. The way to evaluate this integral would be to do a substitution, as is done in single variable calculus, and that is to let x equal to 2 sine theta. Then differentiating this, we get dx is equal to 2 cos theta. So if we just write down the term that's inside the integral, that is the square root of 4 minus x squared, then what this is, there's a dx as well. This is equal to the square root of 4 minus 4 sine squared theta, because of course the x squared, multiplied by dx, and dx is 2 cos theta d theta. So simplifying this, we just bring out 4 as a common factor inside the square root. So that gives us 4 into 1 minus sine squared theta times 2 cos theta d theta. We know from our laws of trigonometry, or rather our trigonometric identities, that sine squared theta plus cos squared theta is equal to 1. So I could just write that along the side. Sine squared theta plus cos squared theta is equal to 1. So cos squared theta is equal to 1 minus sine squared theta. So this part is simply cos squared theta. So we have the square root of 4 cos squared theta times 2 cos theta d theta. Square root of 4 is 2. Square root of cos squared is cos. So square root of 4, that's 2. 2 times 2 is 4. And cos theta times cos theta is cos squared theta. So there's just one more trig identity to remember, and that is cos 2 theta. So you'd remember that cos 2 theta is equal to 2 cos squared theta minus 1. So if we just solve for cos squared theta here, then we get that cos squared theta is equal to half 1 plus cos 2 theta. So we're just going to substitute that in as well. So the 4 times the half is just going to give us 2. So we have 2 into 1 plus cos 2 theta. d theta. So this is what our integral becomes. And of course, we're integrating a circle. And if we're integrating from 0 to 2, it means that we're integrating in the first quadrant. So the first quadrant simply corresponds to 0, so 0 to 2 just corresponds to 0 to 90 degrees, and 90 degrees is of course pi over 2 radians. So our integration bounds become 0 to pi over 2. So we're just going to substitute everything into our integral. So our integral now becomes this minus 4 multiplied by 2 gives us minus 8. So it's minus 8 times the integral from 0 to pi over 2 into 1 plus cos 2 theta d theta. Then integrating this, it becomes minus 8 into, well, the integral of 1 is just theta, and the integral of cos 2 theta is, well, the integral of cos is sine, but also remember that we have a function within a function, so we have 2 theta. So sorry, I neglected to write the 2 theta here. So to cater for this 2 that's inside the sine, we have to put a half in front. And we're integrating from 0 to pi over 2. So when we do that, we get minus 8 into pi over 2 plus the integral of sine of 2 times pi over 2. So 2 times pi over 2 is just pi. Sine of pi is just 0. So this means that the final answer is simply minus 4 pi. So this whole long protracted example was just to show that we're integrating along a curve. This is the line integral along a curve. And when we do that, we have to split up our curve into 2 parts if it's not a single valued function, as was the case in this example.